Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzuddin bin Izlan, and today I will present about my final year project entitled Manufacturability of Water Purification System from Biowaste under the supervision of Dr. Abdul Manaf bin Abdullah. So the content of this presentation are abstract, introduction, objective, methods, result and discussions, and conclusion and recommendation. Let's begin by the abstract of this study. Nowadays, water purification systems are one of the most significant systems that must be used on a regular basis. The goal is to achieve cleansed and disinfected water that may be used for several purposes, such as human consumption, medical treatment, and industrial applications. The abundance of biowaste throughout the community nowadays has become an environmental concern. Therefore, this project intends to turn selected biowaste, which is eggshells, into an affordable water filtration system. Nonetheless, the efficacy of the filtration needs to be investigated to warrant its function. Next, for the introduction of this study, water is essential to the human in their daily life because water comprises approximately 75% of the human body and is essential for life and bodily homeostasis. Clean water is also required for the prevention of different diseases such as waterborne disease that are easily transmitted because drinking water systems are unsafe for human consumption. The abundance of eggshell biowaste is becoming an environmental concern. Alternatively, the eggshell biowaste could be turned into a water filter. However, the eggshells need to be thermally treated to remove any organic residue. Based on the past research, the eggshells were placed in an oven for 2 hours at 900 degrees Celsius. At this temperature, the eggshells will turn into calcium oxide by liberating carbon dioxide. Numerous studies assess the use of eggshell waste as an absorbent, fertilizer, and for other medical purposes. However, eggshell-based water filtering systems is yet to be explored. In addition, current water filters are relatively expensive, making them out of reach for the majority of people. Based on this study, the main objective is to develop a water purification using biowaste, which is eggshell. In particular, the eggshell will be used as the precursor for the creation of a water filtration system by converting eggshell waste into a powder to be used as a filler with a combination of porcelain. The objectives of this study are to evaluate the effect of sintering temperatures on the physical and phase characteristics of eggshell-based composites. The study was carried out to assess the effect of sintering temperatures on the mechanical and morphological properties of the composites. Now, let's moving on to the methods of the study. This flowchart indicates the methods of the study. Firstly, the collected eggshells and porcelain were grinded to transform into powder form. The powder of the eggshell and porcelain was sieved to obtain the particle size of less than 250 micrometer. The sieved eggshell and porcelain powders were mixed in a ratio of 20 to 80 respectively before ball mill for 3 hours at 350 rpm speed. After ball mill, the powders were filled in a mold with a diameter of 8 mm and pressed at 1000 kg with a holding time for 20 seconds. The additional samples also was prepared for the XRD analysis with 25 mm of mold diameter and pressed at 10,000 kg without the holding time. Then, the samples were sintered at 900 degrees Celsius for 3 hours with a heating rate of 26 degrees Celsius per minute. The sintered samples from 900 degrees Celsius were sintered again at the temperature of 1000 degrees Celsius and 1100 degrees Celsius for 2 hours with the same heating rate. After the samples were prepared, the characterization was divided into two parts, which are physical and phase identification and mechanical and morphological properties. The physical characteristics such as volume, density, and linear shrinkage are deemed significant since they might affect the filtration system's efficiency. SRD analysis was used to identify any unidentified crystalline phases produced by varying sintering temperature with the measurement conditions of 40 kV and 40 MA X-ray, 2 degree per minute for scan speed, and 2 theta scan exists with a scan range of 10 to 80 degree. For the mechanical and morphological properties, the Shah hardness was applied to test their hardness. The compressive test was applied to identify their strength and elastic modulus with a set of 1 mm per minute crosshead speed. The same image were taken to identify the morphological properties of the samples. The number of samples for physical and mechanical properties evaluation will be 3. So now, what we have for the result and discussion of physical identification, the volume of the sintered samples decreased about 10.75%, 0.87%, and 27.58% after sintered at the temperature of 900, 1000, and 1100 degrees Celsius. This is because the eggshells are calcined at a high temperature for hours that cause the reduced number of micropores of eggshell. The density was decreased after sintered at 900 degrees Celsius. This is because the degradation of porcelain calcite causes pores and capillaries to open, which generating vitrification and carbon dioxide emission. The viscose phase retains gas inside closed pores, decreasing sample density. The density was increased after sintered at 1000 and 1100 degrees Celsius because solid-state sintering bonds and densifies particles using heat below the material's melting point. Sintering reduces the compact's free surface area and increases density. For the linear shrinkage result, the sample linear shrinkage was 11.07% at 1100 degrees Celsius, which is the largest linear shrinkage percentage, 0.26% at 1000 degrees Celsius, and 3.92% at 900 degrees Celsius. Previous research found that when sintering temperature increased, sample linear shrinkage increased. For the phase identification results, there were 5 samples that had been tested for SRD analysis, which are 3 sintered samples at the temperature of 900, 1000, and 1100 degrees Celsius, unsintered porcelain, and calcium oxide. All the results were plotted and summarized in the graph. Based on the results, we can observe that the element of porcelain was more than the element of calcium oxide for each of the sintered samples. This is because the mixing ratio of the porcelain was higher than calcium oxide, which is 80% porcelain and 20% eggshell. The element of calcium oxide only can be seen at the temperature of 1100 degrees Celsius. The presence of moisture in the air facilitated the hydration of calcium oxide to calcium hydroxide, resulting in portlandine in calcined eggshell powder. Let's moving on to the mechanical properties results. Based on the results of Shah hardness, the difference in the hardness value could be due to sintering temperatures and transformation of calcium carbonate into calcium oxide. According to the literature, hardness increases with eggshell percentage in matrix material increased. Sintering temperature and compaction pressure affect material's hardness. For the compressive test results, the compressive strength increased with the increase of sintering temperature due to the formation of a dense structure. The sample started to fracture when the curve of the graph passed the maximum stress. For the morphology properties result, the same image of the sintered samples were taken at the magnification of 3000. The morphology of the sintered samples at 900 degrees Celsius and 1000 degrees Celsius were almost similar, but when comparing with 1100 degrees Celsius, the changes in their surface morphology could be clearly observed. This was due to the difference of surface compactness of the sintered samples. The morphology of the surface at 1100 degrees Celsius was more compact compared to the synthetic samples at 900 degrees Celsius and 1000 degrees Celsius. The compressive strength was affected by the compactness of the sample's surface. The compact the surface, the higher the compressive strength. This could be one reason which explains that the compressive strength of synthetic samples at 1100 degrees Celsius is the highest among the others. In conclusion, the actual biowaste can be reused and utilized as an affordable water filtration system since it had potential to give more benefits to the human and environment. The element of porcelain was more than the element of calcium oxide in every various temperature of the synthetic samples since the mixing ratio of the porcelain was higher than calcium oxide. The higher the centering temperature, the higher the compressive and modular strength, the compact the surface morphology. Lastly, for the recommendation of the study, the identification of thermal characteristics and the assessment of ion leaching should not be ignored, since they will affect the filtration system efficacy. That's all from me. Thank you.